Hello everyone. Thank you for attending our final year project presentation. I'm Eve, and here's my partner Julia. The product we designed in our final year is a star search engine. The aim of this product is to find attractive faces around us. You may wonder, is beauty an objective concept? Well, based on recent research, we learned that beauty actually is machine learnable. Therefore, we utilize the AI technology to do facial attractiveness prediction. Furthermore, we made a desktop application using Node.js so that users can play with it. And first, I'd like to talk about the dataset we used. In this term, we enlarge our dataset. It contains 5,500 frontal faces with diverse properties. There are 2,000 Asian female faces, 2,000 Asian male faces, and also 750 Caucasian female faces and 750 Caucasian male faces. Their ages are all within 15 to 60. The portraits have no accessories or other distracting items such as jewelry. All the images are labeled with beauty scores ranging from 1 to 5 by totally 60 volunteers aged from 18 to 27. And here, the beauty score 5 means most attractive and so on. And below is a sample of our dataset. You can see from this picture that these faces get a score of 5, which means they are most attractive to others, and faces like these ones only get a score of 1. So that is about our dataset part. And besides renewing the dataset, in this term we also introduce a new technology, which is camera calibration. In order to capture attractive faces around us, the tool we used is a 360-degree camera. However, the images captured by it have certain distortions. As you can see from the picture on the left, the lines on the scaling and also on the chessboard, there are severe distortions. And as our attractiveness rating algorithm relies on the geometric relationship of facial landmarks, faces distortion may affect the accuracy of attractiveness rating. So to reduce the distortion impact, we conducted image calibration using algorithms introduced by the Python CV2 library. The inputs of the calibration algorithm are a 3x3 matrix which contains camera parameters such as focal distance and a vector which contains 5 distortion coefficients. We input these inputs into the algorithm, and here on the left is the output. You can see on the scaling and also the chessboard that distortion effect has been removed. And next, my partner Julia will talk about the methodology we used.
I will introduce our methodology in these projects. To establish communication with the 360-degree camera Ricoh Theta V, we use the latest Ricoh Theta API version, which conforms to Google Open Spherical Camera for app development against spherical camera. With the connection of camera with built-in Wi-Fi, we send HTTP post requests to control the camera remotely from our desktop app. We use command camera.takePicture to request the camera to take a picture, and use command camera.list files to download the image to our local storage for image processing in later steps. After we obtain the 360-degree image, we perform face detection with DLive Facial Landmark Detector. DLive contains a pre-trained model of facial landmark detector to locate the coordinates of 68 facial landmarks, which can describe the shape of facial regions such as mouth, eyes, eyebrows, nose, and jawline. DLive supports multiple faces detection. It is fast and accurate, which is suitable for our projects. As for data representation, based on previous psychological research, facial attractiveness can be represented by the geometrical relationship of facial landmarks. Therefore, we calculate the facial ratio of various facial landmarks to represent the attractiveness of a face. First, we extract 19 key points from the 68 DLive landmarks so that we can use less points to represent face regions. We get all combination of 4 points, which is in total 3,876 combinations. For each combination, we calculate 3 different distance ratios. First, we can use 11,628 ratios to represent facial features as our training input.
And after we get our training inputs, we can start to train our models. In machine learning part, we try two models. The first one is ResNet 50, which is a 50-layer ResNet. And ResNet is the short name for residual network, which means it is a network for residual learning. Different from a deep convolutional neural network who learns several low, mid, high levels of feature at the end of its layers, residual learning networks try to learn some residue. Residue can be simply understood as subtraction of a feature learned from input of that layer. ResNet does this using shortcut connections. It directly connects input of nth layer to some n plus 6th layer. And the second model we used is the linear regression model. After comparing the execution time of these two models, we chose the faster one in the end, which is linear regression. And then we used A2 split to test the result. Among 5,500 images, we used 80% of them to train our model and the remaining 20% as the testing set. As you can see from this chart, the red line represents scores given by the 60 volunteers, and the blue line is the prediction of the model. The correlation between the red line and blue line is about 0.63. And up to here, we have finished the facial attractiveness prediction part. Now, Julia will introduce the implementation of desktop application.
We developed an Electron desktop app as a star search engine. Electron is an open source library for building cross-platform desktop apps with HTML, CSS, and JavaScript. It combines Chromium for front-end and Node.js for back-end. The reason why we develop with Node.js is because our attractiveness prediction algorithms rely a lot on Python scripts, and Node.js support interaction between JavaScript and Python, so that we can reuse our Python scripts last semester. The workflow of our desktop app is like this. The application will start with the press of the start button. First, it will request the camera to take the picture with Ricoh Theta API and get the latest image URL with another API call. When the URL is received, we'll download the image to the local storage and then call the Python script. The Python script is our attractiveness predictor, which includes face detection, facial features extraction, and regression model. The Python script will return the rating of faces, which will be displayed on the screen of desktop app. Then it will instruct the camera to take a picture again. The loop will be played continuously until the stop button is pressed. Now that we can demo our project, the camera will be placed in the middle of the public area with lots of people. When we press on the start button, Ricoh Theta will start to take pictures. Then it will show the image without rating first. After a few seconds, the rating result will be displayed. As we can see, the face capture is highlighted with the score marked above the faces. The left corner shows the number of faces and whether an attractiveness face is found. We use score 3.7 as a benchmark to define attractive face, as 3.7 is higher than around 80% samples in our datasets. That's all for our presentation. Thank you.